So, one place that exponential growth can be used a lot is medicine. There's a lot of things in medicine where this can be used. So, whether it is analyzing, like the spread of a disease, like currently everybody's really paying attention to the coronavirus, or it could be medicine that your body is using up at an exponential rate. So it's a place where this is used a lot. So in this first example, of course, everything we're going to have is overly simplified because you guys are juniors in high school and not medical researchers yet. And let's face it, I'm not even a medical researcher. So this is a little overly simplified, but it's the idea behind a lot of it. So initially, 750 virus particles infect a person. The virus replicates at a rate of 157% per hour. How long will it take for the virus population to grow to 5 million? So there is a possibility, or let me say this about these problems. There is the possibility to either use just regular exponential growth or continuous exponential growth here. And if you use, each one's going to give you a little bit different answer whenever you do this. If you are an actual medical researcher, you would kind of have a lot of data on this and see which one fits your data the best. For me, if I want you to use the E formula, I'm going to put the word continuously somewhere in the problem. So I did not say continuous growth anywhere here. So we're just going to use regular exponential growth for this one. So that, for what I'm going to give you on homework quizzes test, that is basically what I'm going to go by. If I mean for you to use the PERT formula, I'm going to say continuously somewhere in there. So this one's just regular. So we're going to have y equals our initial amount right here, 750. And so this virus is replicating at a rate of 157%. So what do I need for my B value here? Very good. 2.57, which is like what Matthew was saying, was confusing him a little bit on the homework last night, because you're taking that 157% and making a decimal, but you still have to add 1 to it. So 2.57, a lot of times I'll see 1.57 there, which is not correct. And that's raised to the x power. And this growth rate is per hour, which tells me that this x right here is in hours, right? So we want to know how long it will take for the virus population to grow to 5 million. So we need to plug in 5 million. Let's see. Zach, where will we plug in that 5 million at? It goes for the y here, because that's our amount. The x is time. It does not go there. So I've got 5 million equals 750 times 2.57 to the x power. Elijah, what would I do to solve that equation there? Very good. So I'm going to do that over here on my calculator. Okay, so I get 6,666.6 repeating equals 2.57 to the x. What next, Elijah? Okay, so whenever I have a base and an exponent raised, I need to get rid of that base. What's the opposite of an exponential? It's a log. So we're going to do log base 2.57 and log base 2.57 on both sides, which is just going to cancel over here, so you just have your x. And then to do log base 2.57 of 6,666.6 repeating, I'm going to do log of, and I can just do second negative. That'll do the answer on the line before. That way I don't have to put in tons of sixes. Or if you don't do that, make sure you put in tons of sixes there in the top part. Divided by log of 2.57. And it is going to give me 9.328 hours. And, of course, this is just a generic problem that I came up with that has no medical research behind it whatsoever. But if you were actually looking at, for example, coronavirus, you would be really interested in this initial value right here, which a lot of times they'll call the viral load. So that's how much you get infected with at the beginning. Because if you encounter, let's say, 50 virus particles, it might not even make you sick. But if you reach this certain like viral load, then it's going to start to make you sick. They think that if you encounter more virus in the beginning, that you'll get sicker, possibly because you have more virus before your body can contain what's happening there. And then you would also be very interested in that replication rate, because it's an exponential growth formula, so you'll see, I'm just going to look at this on Desmos just because it's easier to see than the graph. So, like if I type in the equation that we're dealing with here, y equals 750 times 2.57 to the x, and I'm going to change my y-axis here to go up to 5 million. You can see here that here's where we're initially infected with 750 virus particles. It's growing exponentially, but at first it's growing really slowly. You don't feel bad at this point, right? But then it's going to really take off at this point, which is where you really need your immune system to come in and start killing it off, right? Because if it just goes up forever, then you're probably going to have some major problems. So you would be studying all of this if you were looking into this, trying to figure out this. And this is some of the math that is behind why they say that you need the certain time frames of quarantines, right? And a certain protocols that you go through. They're looking at all of these things. I wish I knew more about it to understand it even better, instead of just hearing recommendations and wondering why. Of course, it probably wouldn't be beneficial in general for them to give you a whole math research paper on why you need to stay at home for this amount of time or whatever, but because the general public would not be interested. But I think it's really interesting stuff. So, let's go on to the next problem. These were actual numbers a couple years ago, I believe, is whenever I took this. I should probably cite my sources, but I'll be honest, I just Googled it, but I think it's probably pretty accurate. So, at least a couple years ago, the population of India was 1.353 billion people. And it was growing continuously at a rate of about 1% per year. So we want to know what will the population of India be in 20 years. So to do this problem, I do see that word continuously, so that tells me that I want to use the P e to the RT formula. And in this case, you got a couple options on how you do that principle. I do not want to have to put all the zeros for billions and type it all in. So I'm going to leave it 1.353. But I need to remember that my answer is in billions of people, right? So when I give my answer, I'm going to write that down. And so I have e to the 0.01 is my rate. Because that 1%, I got to move that decimal 2 places for this. For the PERT formula, you do not add 1 to that. It's just the interest rate or the growth rate as a decimal. And then that's multiplied by time, which is 20. This is a pretty straightforward problem. So we got 1.353 e to the 0.01 times 20. And so I get 1.6525. I'm going to just go 5, 6 there, but if you want, let's just do 1.653 billion people. So if on a quiz or a test on this, you would, if it's in Canvas, I'm probably going to have to just have you put the whole number in, like move that decimal and make it billions. Or if it's on paper, make sure you write billion beside of it here. The other option, of course, is you could use all the zeros, and that would be fine for that. %1 does not sound really like a super high growth rate, but you can see that in 20 years, which is not that long, that you've got 0.3 billion extra people. Maybe we do need to move the decimal place just to see that. So we got 9 decimal places per billion. Sometimes you just need to see all the zeros to really appreciate how many that is. 300 million people. That's a lot of people. That's the population of the United States, more or less. Right? It's about 300 million, I think. I think it's close to that. So, it's a lot of people. It doesn't look like it's that much whenever it's decimal places, but it's a lot of people. Okay. Yes? Okay. This is a side note. This is just well, I need to know. I'm going to ask you that later. I need to ask you that. It's not related to this. I'm going to ask you. Maybe a warm-up sometime. Alright. Example 3. In 2000, the population of wolves in a certain area was 457. The number of wolves increases exponentially at a rate of 3% per year. Predict the wolf population in the area in the year 2025. So, this one does not say continuously anywhere, so we're just going to use the regular exponential growth formula. So, our initial value is going to be 457. We've got a 3% growth rate, so we got 1.03. And in this case, what am I going to use for my time here, for my exponent? What will we use, Matthew? Okay, 25. Sorry, you guys, I need to move one of you over here, so if I point, it doesn't look like it's the same one. We use 25, not 2025. Be careful. A lot of times people want to put that year in there. So you just need to type this one in. And so we would get 956.857. However, since this is wolves, you can't have part of a wolf, not a living wolf anyway, so let's just round this to 957 wolves. Yeah, and usually I will put at the bottom, round to the nearest wolf, or something like that, so that you know what to round to on that. If I don't say anything about rounding, typically you're going to use 3 decimal places for that, but I try to, on these, remind you it doesn't make sense to use 3 decimal places in this case. So another thing, like if it's money, I will typically only round to 2 places with money. So I'll probably say round to the nearest cent on those. If you ever have a question on the quiz or test, just ask me what to round to on those all. I forget to put it. Yes. So tomorrow you got 2 things that'll be on the quiz. It's going to be domain, range, all of that stuff, and then you've got the exponential stuff that'll be on there. Okay, so the population of Italy can be modeled by this equation, where T is the number of years since 2018. How long will it take for Italy's population to drop below 60 million? So you can tell for this one, it has a negative rate right here. So the population of Italy is decreasing, which is also true. I think I looked up these numbers as well. Italy's population is decreasing over time. Most people having fewer, or most couples having fewer than 2 children. So lots of couples with 0 or 1 child, not very many with 3, 4, or 5. So the population is going to decrease because of that. For this, we want to know when it will drop below 60 million. So we would have to put 60 million over here and set that equal to our equation here. And so, Manuel, what will I do to solve this equation? Okay, so what we're trying to solve for is the time, so we're trying to get to this over here. We want to start furthest away from that, which is going to be this 60,360,000 right here. How could we get rid of that value? We're going to divide it off. So we're going to divide by 60,360,000 here, and so alright, so I'm getting 0.9940357. Keep that whole number in your calculator. It's fine if you don't write it all down, but keep it in your calculator. And this is e to the negative 0.002t. So, Manuel, what do we do to get rid of that e next? Good. We're going to natural log both sides. Whenever you do this, make sure you do natural log and then do second negative key to do the answer there. If you have the really fancy new ones, you might can go up and hit enter and it'll paste it down there, but I know that some of the school ones do not do that. And so that gives us negative 0.00598 and so on is equal to negative 0.002t. And Manuel, what's the last thing we're going to do here? Perfect. And so if we do that, we are going to get 2.991 for our t. So 2.991 years. So if everything began or stayed like it was, population would be below 60 million in 2.991 years. Just give a quick Google. See what it's at. That's 2019. It's not. That's what I used. I don't know how accurate this is. Doesn't look like things are changing much. I don't know if those are accurate though, because this says live, but they also have a Circle K gas station ad up here at the top, so I'm not sure how accurate that is. So, let's see. Yes.
I rounded the 60 million divided by 60,000 and 60 million and 60,000.
Uh-huh.
And I rounded up the number to 0.994. I got 3.209.
Yes. So on these problems, that you want to save that whole number there instead of rounding, because we don't want to round until we're at the very, very end. So you don't want to round to 3 places during the problem, because especially with exponentials, it will throw your answer sometimes way off because that error that you have by rounding is multiplied because it's exponential. So yeah, it would be counted off. So so what you want to do instead is, there's a couple things you can do. If, like we had this whole number right here, if you press second and then the negative key, it gives you the number that's on that line before the answer. So that's one thing you can do. Another thing you can do, you guys know how to store values? There's going to be some times where this is helpful. So let's just say we had 5 divided by 7 for some reason. Okay, I got this decimal. It goes on forever here. So if you click this button right here above on, if you tell it to store, STO and the arrow, it's going to say answer and put an arrow here. And then you can store it as a letter. Any letter is fine. I usually don't use X, but otherwise, like if I want to store it as A, then it would be stored there. So that's another way you can do that same thing. That might be helpful if you know you got like a number that you're going to need to use a lot later on. There, you probably don't have to do that for this, but it's another option. Mm-hmm.
So when you're doing what it says, how long it takes to drop below, then could you not do like 59,999,900?
I see what you're saying.
Taking, instead of like doing equals like the
right, equal to
literally just minusing 1 for so it's below it.
You don't have to do that. Because what's going to happen, it's going to be, you are correct, it's going to be exactly 60 million. But because this is continuous growth, like the instant after that, it's going to drop. So it's okay with me. You don't have to think through that far. So you can just use 60 million exactly. That's fine. And even if it's not continuous growth, even if it's yearly growth, it's still okay, because whenever you think about like the graph, it's still smooth. Okay, half-lives. Half-lives are something we haven't looked at much yet. Have you guys seen that term half-life before? Okay, seen it in, have you seen it in biology? And have you done it in math before? Think so, maybe. All right, so who can tell me what a half-life is? Oh, no, I've already, never mind. I need to read my problem before I ask you that. Because it tells you the half-life of a substance is the amount of time it takes for half of the original amount of the substance to decay. So your definition of your half-life is right here at the beginning of the problem. It may or may not always say that, but sometimes it does. A lot of times if you see like ACT problems, they'll start off with that. They'll tell you what a half-life is. So half-life of a medicine, it shouldn't say medicine and substance. or a substance is 4 hours, how much medicine will remain in the bloodstream after 13 hours if the initial dose was 800 milligrams? So the idea with half-life is this, and half-life is something that you'll see a lot for radioactive decay and for medicines or any type of chemical in the body, right? Because your body, this is the way that it breaks this down. So time in hours and amount. So if you take 800 milligrams at 0 hours, you have 800 milligrams in your system, right? So what's going to happen every 4 hours, half of that is going to be gone. So after 4 hours, you would have 400. And then after 8 hours, so that's another 4 hours, how much would you have left? 200. What about after 12 hours? 100. After 16 hours? 50. And after 20 hours? 25. Right? And this would keep on going, right? So it would diminish. Because your body is filtering out whatever medicine that is. So your kidneys or your liver or whatever deals with that particular type of substance is filtering it out, but it's not getting every bit of it, right? So, theoretically, is it ever gone? Theoretically, it's never gone. Because at 24 hours, you're 12.5, and then at 28 hours, you're at like 6.25. And this is just going to get smaller and smaller. It'll be tinier and tinier and tinier and tinier and tinier decimals. Theoretically, it's never gone. Now, in actuality, if you took an ibuprofen, 4 hours ago, eventually it's going to be non-detectable levels in your system. Now, I don't know if maybe you do have like a teeny, tiny particle still floating around in there somewhere years later, but it's not going to be detectable, right? So it stays in your system for a lot longer in tiny, tiny, tiny amounts. This is why if you were to ingest or smoke certain illegal substances, you can still detect it most of the time up to a month after you actually partake in said illegal substance, right? So if you get drug tested, it might be 3 weeks ago whenever you did whatever it was that you should not have done, but they can still tell. They can still tell that's in your system. Now, if it's been 2 months, then it's not detectable anymore, and they're probably not going to be able to tell that that occurred. But if it's within whatever time frame for your sensitivity there, it would be different for different substances, but typically with drug tests, they generally say about a month they can still detect levels of illegal substances there in your body. So, like, you might have partaken of said illegal substance 3 weeks ago, which you guys would never do. I know you're not going to. But someone might. And they come to school 3 weeks later and they get drug tested. They are not high at all, right, anymore, because they don't have any they only have detectable amounts in their system, but they are not actually under the influence of it at that time. But you can still tell that it's there. So that's, how that works. So, now we made this chart. Does it answer our question? Not very specifically. I can at least tell it's somewhere between 12 and 16 hours, right? Somewhere between 13 hours is what I'm looking for. I can tell it's between 150, right? Somewhere between 50 and 100 is how much is left, but it doesn't give me a specific answer. So we need to set up an equation to have a more specific answer, because if this is an ibuprofen that we took and we're wanting to take some more, that's negligible, not that big a deal if you're off by 30 minutes or so on taking that ibuprofen, especially if it's just a one-time thing and you're not taking it daily for long amounts of time. However, if this is anesthesia they use to put you under, whenever you're having a major surgery, it matters a lot how close they are. I had to have like an outpatient procedure several years ago, and the doctor that was explaining, everything to me before the surgery said the anesthesiologist would be there. They would use, I can't remember the name of the drug, but they'd use this drug to put me to sleep. And then he says, this is Michael Jackson's drug of choice, which was not a nice thing to say to somebody who was about to take this drug and be put under and did not want to die like Michael Jackson did from this stuff. So if you're dealing with really high-powered stuff, it is really important that you get this right. You need to know the body weight of the person and how fast they're going to metabolize this. And there's probably going to be differences between male and female and all of this stuff, because you got to get that right, because the stuff you're giving people can easily kill them. Ibuprofen could kill you, but you're going to have to take a whole lot of it. All right. Taking one extra pill is probably not going to do you in right there. But if you're dealing with that high-powered stuff, it's a big deal. So this is really important for you to know if you're in that situation. So our equation, we begin with 800 milligrams. We are going to use 0.5 or 1/2 as our decay rate here. The key to this right here is, though, if we do that, how long does it take for half of the medicine to be gone? 4 hours, right? It's not 1 hour, it's 4 hours. So this right here is my number of half-lives. So it is not my number of hours, it's my number of half-lives. Almost. Not 4 divided by 13. 13 divided by 4. So for number of half-lives in 13 hours, I'm going to do 13 divided by 4, which is going to be 3.25. So 13 hours is 3 1/4 half-lives, and that is the number that I'm going to plug in. So I will do 800 times 0.5 to the 3.25. And I get 84.090 milligrams. So that will give me an exact number. If you're, like I said, if you're really in this scenario, there's a lot more to consider than just this. Right, so that's why anesthesiologists get paid a lot of money and they have to go to school for a really long time, because you got all those other factors that are going to matter here too. So they got to, it's not just, your half-life is not going to be 4 hours for every single person. If somebody weighs 100 pounds versus 400 pounds, they're going to metabolize at different rates there. So it adds even another layer in there in real life. Okay. Another thing you're going to see half-life a lot for is carbon dating. So whenever archaeologists go and dig up an ancient civilization and they say that they know that it is 15,000 years old, carbon dating is what they typically use for that. So it's a method that we use for estimating the age of things that are really, really, really old. You would not use this on, something that you find, like a body that died 3 months ago. If you find that in the woods somewhere, you would not use it for short-term things. There's a lot of other things they could use for that. This is for ancient things that we're looking at here. So half-life of carbon-14 is about 5,730 years. A bone is uncovered that has 27% of the original amount of carbon-14. What I don't know about this is how they know what the original amount should be, because I obviously don't know everything there is to know about carbon dating, or that would probably be what I would be doing instead of this, even though I love doing this. But somehow they know that a bone of this size that they have found should have this much carbon-14, but only 27% of that carbon-14 is there. So we're going to use that to estimate the age of the bone. This is a little bit like Alfredo and his money. Do we know how much we started with? We do not. We just know that we have 27% of it left. But it's a little like Alfredo's money. It doesn't matter. It does not matter how much we start with if we know that percentage that we have left. Like with Alfredo, our percentage was half. We knew he had, or not half, doubled, right? Double his money, so 200% of his money. Here we've got half. So we're going to have y equals, I don't know what my original amount is, so I could use 1. I'm going to use 100. I just like it. It's easy to deal with here. But you could use 1. You could use 7.253 if you want, but that's just going to make it hard to deal with. And then times 0.5 to the x power. But remember here, this is number of half-lives. It is not years. It's number of half-lives. And so I don't know how much is left exactly because I don't know how much I started with, but if I started with 100, how much would be left? 27, right? That's why I chose 100 because it's a nice, easy value. So if I find 27% of 100, it's just 27. So I could put 27 over here. 100 is 0.5 to the x power. So now we just want to solve for that x. Ethan, what would we do to solve for x there? Good. Which is just going to give us 0.27. It's 0.5 to the x. And what do we do after that, Ethan?
Put it in like logarithm form.
Good. And what's that going to look like?
Log. Is it base 0.5 to 0.27?
Yes. So you can think of it rewriting, or you're just doing log base 0.5 log base 0.5 here because that log base 0.5 and the 0.5 will cancel out. And so to type this in, we just have to do log of 0.27 divided by log of 0.5. And we get 1.8889. Keep this number in your calculator because this is our answer. Because I just said we would not use carbon dating for something that's only like really young, like 2 years old, right? So what have I got to do here? I've got to multiply this by the half-life because this x is my number of half-lives. So my answer is not in years here, it's in half-lives. So it depends on what the half-life of the material is. In this case, it's 5,730. So I'm going to multiply this by 5,730. Keep that whole decimal in your calculator and just hit times 5,730. And so we get 10,823.790 years. Of course, that would be an estimate. You would probably give a range of dates because we can certainly not know with such precision the actual age of something that's ancient there. I would like to know more about this. If any of you guys know anybody who researches the coronavirus or is an archaeologist that's carbon dating things, anybody ever know anybody of these sorts? You need to put them in touch with me. I need them to come talk to the class so they can tell us a little more about how this really works. I feel like there's got to be some guesswork in this, which is probably why I usually hear that something is between this age and this age. But of course, I've never actually done this myself. Okay, one last thing that we're going to look at, depreciation. This is going to happen. This is actually what happens when you go buy a new car. So sometimes I hear people calling their car an investment. If it is an investment, it's a terrible investment because your car is going to decrease in value if you drive it. Now, if you have like a classic car and you just sit it in the garage and you rub on it a little bit, it might go up in value. But if you actually drive it every day, your car is going to decrease in value, right? You might want to choose a car that does not decrease in value as quickly. Some depreciate much more quickly than others. But your car is not going to be worth what you bought it for 2 years from now. Unless we are in the current economy and everything is skyrocketing, inflation through the roof. And actually, my brother-in-law sold his truck for more than he actually paid for it whenever it was new. But times are crazy right now. That's probably not going to last for long. And if it does, inflation's going to be so bad that we're not going to be able to afford any new cars, so it's not going to matter. But typically should decline, right? So what you see here is if you buy a brand new car, it's going to drop a lot more at first. Whereas if you have a car that's 20 years old, it's still decreasing 11%, but 11% of $2,000 is not nearly as much money as 11% of $43,000, right? And this number right here would be different for every car that you have, and of course, condition matters too there. If you don't take care of it, it's going to be in bad shape. But generalizing here, we got an initial value of $43,000. And the car's depreciating at a rate of 11% per year, so we're decreasing in value. What should we use as our percentage here? 0.89. We're going to get that by doing 100% minus the 11%, which gives us 89%, and then changing that to a decimal. And that'll be to the X power. Now, we want to know how long it's going to take for the car to be worth less than half of its initial cost. So, 43,000 divided by 2 is going to give us 21,500. So, 21,500 is what we're looking at here. And again, it does say less than here, but the nanosecond after this, technically, it's a little tiny bit less, worth less, right? So we'll just set it equal to. So, let's see. Josie, what would we do to solve this? Good. All right, and so we have. And we got 0.89 to the X power. What will we do after that, Josie? Good. Log base 0.89 so that we can cancel out that 0.89. So I'm getting X equals log of base 0.89 of 0.5. And to do that in the calculator, I'm going to type in log of 0.5 divided by log of 0.89. And it's going to give me 5.948 years. So if you had this case, it'd be about 6 years. The car would be worth half of what it started with. Yes?
So this is like the other one where it's no matter what the number is, as long as the rate is the same, it's always going to be the same. Like how it was 2.
You're right. Yeah, so this would be true no matter what the car cost in the beginning, right? So I could ask the same question without telling you how much it cost in the beginning. Yes, that's right. So if you had this same 11% per year deflation, it takes about 6 years for the car to be half price, whether it costs $5,000 or $500,000, right? that gives you an idea there. All right, so that is everything. The assignment tonight is to finish the worksheet that you guys were working on yesterday. So answer key is still up for that, so you can still see that to check your work. You've got about 20 minutes, so hopefully you'll be able to get a lot, if not all of it, done before you go. Let's see what happened to my recorder. Did I start the recorder?
Yeah.
And it's disappeared on me. It's not working like it's supposed to. I thought I had it fixed. It worked fine during first period. Major needs to see this, although it's not the worst day. He might can figure it out. But something's wrong with this.
Like when you're dealing with people or animals, and you get this, and obviously you can't have 0.617. So would you round it down like that, or would you?
I usually just go like round it to the closest. So it's sometimes some people want you to round down, but I usually just take the closest. So I do 1696 for that. If it is like people or animals or something, whole number is the best to round to. If it's money, give me 2 places. Otherwise, just do 3 decimal places. Okay, so you need parentheses around it because what it's doing here, if you don't have the parentheses, it's only putting the point 12 in the exponent, and then it's multiplying the answer by 8. So you need those parentheses